Good morning, everybody. This is Indira, Assistant Professor of Institute of Aeronautical Engineering, Department of Mathematics. In the last session, we have found how to reduce the given matrix into the diagonal form. In this session, we are going to learn how to do the orthogonal diagonalization of the matrix. Let me recapitulate how we have done the diagonalization of the given matrix. In the last session, we have seen that suppose A is a given matrix. A is a given matrix. Then we need to find out the eigenvalues of the given matrix. Eigenvalues of the given matrix. After finding out the eigenvalues of the matrix, we need to find out the eigenvectors for each eigenvalue. Eigenvectors for each eigenvalue. All these eigenvectors have to be set together to frame the model matrix that will represent it by capital P. That will represent it by capital P. Now, P is nothing but the set of the eigenvectors. Let us suppose that I have 3 eigenvectors for 3 into 3 matrix. If I take a 3 into 3 matrix, a given matrix as. Right? Now, in the next stage, we need to find out the P inverse of the matrix. We need to find out the inverse of the matrix, P inverse. Then multiply P inverse with A into P, and which we will get it as a required diagonal matrix. This diagonalization helps you to find out the powers of the matrix, to find out the powers of the matrix by using A to the power of n is equal to P into D to the power of n into P inverse. So this is helpful to find out the powers of the matrix. So this is what we have learned in the last session. Now let's continue with the orthogonal diagonalization of the matrix, which is another part of the diagonalization of the matrix. The diagonalization of symmetric matrices. A matrix capital A is diagonalizable if and only if there is an invertible matrix. There is an invertible matrix capital P such that A is equal to P into D into P to the power P inverse, where D is the diagonal matrix. A matrix capital A is orthogonally diagonalizable if and only if there is an orthogonal matrix P such that A is equal to P into D into P inverse, where D is called as a diagonal matrix. Recall that any orthogonal matrix A is invertible, and also A inverse is equal to A transpose, because we have that. For a matrix to be orthogonal, A into A transpose is equal to A transpose into A is equal to identity. Bring one of the matrix A to the left hand side, or you consider A into A transpose is equal to I. So if you bring this A on the right hand side, A transpose is equal to A inverse. So when a matrix is orthogonal, then A transpose is equal to A. So using this identity, there is no need to find out the inverse of the model matrix capital P. Okay, because in the last session we have seen how to find that the diagonal of the matrix is nothing but P inverse into A into P. Suppose if it is the orthogonal diagonalization, then this can be replaced by P transpose into A into P. So there is no need to find out the inverse of the matrix. Just with transpose of the matrix, it is multiplied with A into B to get the required diagonalization. This procedure is nothing but the orthogonal diagonalization. The formula for transpose of a product M into N whole transpose is equal to N transpose into M transpose. Using this, we can see that any orthogonally diagonalizable A must be symmetric. This is because A transpose is equal to P D P transpose whole transpose. So if you open this, we are going to get it as P transpose whole transpose into D transpose into P transpose, which is nothing but P into D into P transpose, which is equal to A. So if A is a symmetric matrix, then any two eigenvalues forms different eigenspaces are orthogonal. Okay, so the spectral theorem says that an n into n square symmetric matrix has the following properties. A matrix capital A has n real eigenvalues if we count multiplicity. For each eigenvalue, the dimension of the corresponding eigenspaces is equal to the algebraic multiplicity of the eigenvalues. The eigenspaces are mutually orthogonal and A is orthogonally diagonalizable. So now all eigenvalues, not the roots of the characteristic polynomial of a symmetric matrix, are real. Eigenvectors of a symmetric matrix corresponding to different eigenvalues are orthogonal. So now let us find out the orthogonal diagonalization for a matrix. I have taken an example, a 3 into 3 matrix. So let us understand how to find out the orthogonal diagonalization for this matrix. Now, given capital A is equal to row wise 2, minus 1, minus 1, minus 1, 2, minus 1, minus 1, minus 1, 2. Now I'll find out the eigenvalues and eigenvectors for the given matrix. So to find out the eigenvalues, I'll calculate the determinant of A minus lambda I is equal to 0. A minus lambda is equal to 0. So that means I have to replace the diagonal elements by 2 minus lambda, minus 1, minus 1, minus 1, 2 minus lambda, minus 1, minus 1, minus 1, 2. Take the determinant of this matrix and we are going to get the third degree polynomial equation, and which has to be solved to find out the roots of the equation. And let us suppose that alpha, beta, gamma are the three roots, and I'll get alpha is and beta as 3, 3 and gamma is equal to 0. So therefore the eigenvalues are 3, 3, 0. Now, in the next stage, the first stage we have found out the eigenvalues. In the next stage, we need to find out the eigenvectors. For that, we have to take each and eigenvalue there, right? So, and each and eigenvalue have to be substituted in A minus lambda I into x is equal to 0. Each and eigenvalue has to be substituted with A minus lambda I into x is equal to 0, and we need to find out the vector x by reducing this A minus lambda I to echelon form. Okay, so that is how we need to find out the eigenvectors for each one. Now you can say that lambda is repeated twice. So we'll get two cases. The first case, when lambda is equal to 3, we'll get two different eigenvalues, and the second case we'll when lambda is equal to 0, we'll get the third eigenvector. So for lambda is equal to 3, the eigenvector is minus 1, 0, 1, and the another eigenvector is minus 1, 1, 0, and the third eigenvector for lambda is equal to 0 is 1, 1, 1. Right? Okay, so these are the three eigenvectors for the three eigenvalues 3, 3, 0. Right? Now we need to frame the modal matrix for the eigenvectors which we have got. Let us suppose that this is x1, this is x2, and the third eigenvector is x3. Then we have to find out the modal matrix, which is set of the eigenvectors, which is x1, x2, x3. So it can be written as minus 1, 0, 1, minus 1, 1, 0, 1, 1, 1. Now this matrix P is orthonormal matrix, and we can just find out. See, look here, x1 transpose into x2. x1 transpose into x2 is equal to, is nothing but minus 1, 0, 1 into the other matrix, that is minus 1, 1, 0. So if you multiply this, we'll get it as 0 matrix. So we can have this as a orthogonal. I mean, in this way we can find out the vector P is a orthonormal or not. After finding out after finding out the modal matrix, each eigenvector have to be divided with the norm of the vector. So the norm is nothing but the norm of x1. Norm of x1 is equal to under root of this the square of the sum of the square of the elements, its element, that is minus 1 whole square plus 0 square plus 1 square, which is equal to under root of 2. Similarly, you try to find out the norm of x2 because we are doing the orthogonal diagonalization for each and every element of modal matrix P. We need to divide it with its norm. So the norm of x2, which is equal to under root of 1 square minus 1 whole square, plus 2 square plus minus 1 whole square. Okay, and which we are going to get it as root of 6. Similarly, you find out the norm of x3, which is equal to under root of minus 1 whole square plus minus 1 whole square plus 2 square. So which is again nothing but the root of 6. So we are going to get the 3 values, norms, and therefore the p value can be written as minus 1 by root 2, minus 1 by root 2, minus 1 by root 6, 1 by root 3, 0, root of 2 by 3, 1 by root 3, 1 by root 2, minus 1 by root 6, 1 by root 3. So I have got the modal matrix, orthogonal matrix, that is P matrix. Now, instead of going for P inverse as we have done for the in the last session for diagonalization, as P is orthogonal matrix, so there is no need to find out the P inverse. Just the transpose of the matrix is enough. So the transpose of this matrix. What is the transpose of this matrix? P transpose is equal to P inverse, and which will be equal to minus 1 by root 2, 0. 1 by root 2 and minus 1 by root 6, 2 by root 3, root of 2 by 3, 1 by root 3, 1 by root 2, minus 1 by root 6, 1 by root 3. So these three are this is the P transpose. So what is the next stage of the problem? In the next stage of the problem, we need to multiply P transpose with A into P. So P transpose and A, matrix A, that is a given matrix, with the modal matrix capital P. Okay, so if I multiply these three, the matrix multiplication leads to the diagonal matrix with the eigenvalues in its leading diagonal. So 3, 3, 3. Are the eigenvalues which we have got in the first stage. The same thing we will get it in the principal diagonal, that is 3, 3, 3. So this is a required diagonalization of the matrix by using orthogonal matrix, modal matrix capital P. So I will go for the next example. Let us see the next example. Find an orthogonal matrix capital P which diagonalizes matrix A, which is equal to 3, 1, minus 1, 1, 3, minus 1, minus 1, minus 1, 5. Right? So let us take the matrix, the given matrix. The first stage, as usually, the problem runs in 5 steps. In the first step, we need to find out the eigenvalue. In the next stage, we need to find out the eigenvector for each eigenvalue. In the third stage, we need to frame the modal matrix. Okay, and check whether it is orthogonal matrix or not. Okay, after checking that it is an orthogonal matrix, then you find out the P transpose, because here we need the orthogonal matrix. We need to diagonalize by using the orthogonal matrix capital P. So in the next stage, in the fifth stage, multiply P transpose AP, which gives the diagonal matrix, required diagonal matrix. So let us proceed with the very first stage, that is finding out the eigenvalues for the given vector. Let capital A is equal to 3, 1, minus 1, 1, 3, minus 1, minus 1, minus 1, 5 is a given matrix. Now, how to get the eigenvalues? Eigenvalues are obtained by calculating the characteristic matrix obtained by taking determinant of A minus lambda is equal to 0. So, the characteristic equation of A is given by A minus lambda is equal to 0, where A is a given matrix, lambda is the eigenvalue, and I is the 3 into 3 identity matrix. So, instead of as a solution is very lengthy, instead of substituting A, I and getting the characteristic equation, is better to replace the diagonal elements of the determinant by 3 minus lambda, 3 minus lambda and 5 minus lambda, and calculate the determinant of the given matrix. So here I got that the A minus lambda determinant as 3 minus lambda, 1, minus 1, 1, 3 minus lambda, minus 1, minus 1, minus 1, 5 minus lambda is equal to 0. Now calculate the eigenvalues for the given matrix by expanding. So the eigenvalues are 2, 3, 6. Here you can see that all the 3 eigenvalues are distinct eigenvalues. Now we need to find out the eigenvector for each eigenvalue here. So in the first stage, I'll find out the eigenvector for eigenvalue lambda is equal to 2. So for lambda is equal to 2, we need to find out A minus lambda I, that is nothing but for lambda is equal to 2, I have to substitute the lambda value in A minus lambda I into x is equal to 0, where x is the required eigenvector which we need to find it out. So this is nothing but it's the 3 minus lambda, 1, minus 1, 1, 3 minus lambda, minus 1, minus 1, minus 1, 5 minus lambda into the matrix, that in the eigenvector that we need to find out x, y, z, which is equal to 0, 0, 0. Right? Okay. Now you substitute lambda is equal to 2 here. Put lambda is equal to 2 here. So we are going to get it as 3 minus 2. 3 minus 2 is 1. 1 minus 1. 1. 3 minus 2, that is 1, minus 1, minus 1, 1, 5 minus 1, the 5 minus 2 is nothing but 3. So we are going to get the matrix in this form into x, y, z is equal to the 0 matrix, 0, 0, 0. Now we'll consider this matrix and try to reduce to echelon form so that we can have the backward substitution to get the values of x, y, z. So that is what I have done here. I've got it as this matrix as minus 1, 1, minus 1, 1, 1, minus 1, minus 1, 1, 3. So the minus 1, minus 1, 3. Minus 1, minus 1, 3. Done. Okay. So it now here, look here. R1 and R2 are same. So R2 you can have, R2 can be interchanged as R2 minus R1. Right? And R3 can be replaced as R3 plus R1. If I do these row operations, it is reduced to echelon form. That is 1, 1, minus 1, 0, 0, 0, 0, 0, 2. Interchange this. Okay, interchange this R2 and R3 in the next stage. In the next step, so 1 minus 1, 0, 0, 2, 0, 0, 0. Okay, now suppose that this is x, y, z. So what is the linear equation that we have got? X plus y minus z is equal to 0, and here z is equal to 0 from the second stage. Okay, z is equal to 0. So let us suppose that y is equal to some k1, then implies that x is equal to, you substitute here, z is equal to equal to 0, y is equal to k1. So x is equal to minus k1. So therefore, the first eigenvector for lambda is equal to 2, we are calculating, isn't it? So eigenvector which is equal to x, y, z, I got the 3 values, that is nothing but minus k1 and 0. So you take k1 as common, so you are going to get it as minus 1, 1, 0. So this is the first eigenvector for lambda is equal to 2. Lambda is equal to 2. So now let's go for the next eigenvector, that is for next eigenvector is 3. Lambda is equal to 3. Okay, substitute in a similar manner, we are going to get it as for a minus lambda a minus 3i, a minus lambda I. So lambda is equal to 3, we are substituting. So a minus 3i, which is equal to 0, 1, minus 1, 1, 0, minus 1, minus 1, minus 1, 2. Okay, and which upon proceeding and reducing to echelon form, I got this as, right? Here, this you can write this as, suppose if this is x1, x2, x3. So I got x1 minus x3 is equal to 0 and x2 minus x3 is equal to 0. Now you solve these two, to get the second eigenvector, and that eigenvector I got it as 1, 1, 1. So x2 is x2 is equal to 1, 1, 1 is eigenvector for lambda is equal to 3. Now I'll go for the next eigenvector, that is finally for lambda is equal to 6. For lambda is equal to 6, I'll proceed in the same manner. So I am going to get it as, I'm going to get this a third eigenvector as minus 1, minus 1, 2. So I have all the 3 eigenvectors in my hand, that is minus 1, minus 1, 2. So you can frame the matrix P, which is equal to minus 1, 1, 1, 0, 1, 1, 1, and the third eigenvector, the set of the 3 linearly independent vectors to make the modal matrix. Okay, so which is this is a P value, right? And I'm doing the orthogonal diagonalization. So I'll find out the P inverse, P transpose for this, P transpose, and before finding out the P transpose, we need to divide it with each and every vector with the norms. So what are the norms? So here this is x1. Let us suppose that this is x2 and x3. Find out the norm of x1. Norm of x1. Norm of x1 is equal to 1 minus 1 whole square plus 1 square plus 0 square, which is equal to root 2. So similarly, the norm of x2. Norm of x2 is equal to under root of 1 square plus 1 square plus 1 square, which is equal to 3. Root of 3, and the norm of x3, which is equal to 1 minus 1 whole square plus minus 1 whole square plus 2 square. Okay, 4, 5, 6. So root of 6. So we divide the first thing with the root 2, and the next the vector with the root 3, and the third vector with the root of 6. Root of 6. So we are going to get the normal normal matrix as P is equal to minus 1 by root 2, 1 by root 3, 1 by root 6, 1 by root 2, 1 by root 3, minus 1 by root 6, 0, 1 by root 3, 1 by root 3. Now, I already said that we can just find out the P transpose multiplied with A and P, because P is an orthogonal matrix here. There is no P transpose is equal to P inverse. So P inverse A P, which gives the required diagonal matrix with the eigenvalues in its principal diagonal, that is 2, 3, 6. So this is how we can find out the diagonalization, the orthogonal diagonalization for the given matrix. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.